we go here. I'm gonna click our button and we are live. Okay, great. Welcome everybody. So this is session 4 of Ultralytics Live, and I'm here with Michael Goin. Actually, I can never get his name right. Michael leads product engineering at NeuralMagic. He works cross-functionality on designing, optimizing, and shipping software for high-performance computing applications. Michael applies cutting-edge optimizations to deep learning models and inference software with the goal of making deployments more efficient and more performant, which is something that I think we would all like to see. And on the other side, we've got Glenn here. That's me. So I'm the founder at Ultralytics and better known as the YOLO V5 author. So the format of this live session is that we are going to chat a little bit about YOLO, chat a little bit about Ultralytics and NeuralMagic, and explain our recent partnership and how you can use NeuralMagic tools to accelerate inference on deployed YOLO models. So when I came into AI, Michael, I was more concerned with, I'd say, just getting my code to run, just getting a model to train, and then getting decent accuracy. But of course, once you're at a point where you can get that, then the next obvious step is, how do I actually use this in the real world? And for me personally, that's always been one of my main priorities, to sort of take ML research out of the lab and into the sunlight and get it into people's hands. And of course, a key component in that is making these models faster. ML models use a lot of operations, a lot of flops. Even the small models require intensive compute. And that's been a problem since the early days and even recently. Even with all the hardware advancements out there, it's difficult to get a model to run as fast as you want. Or if you do, you might want to run it at a slightly larger image size. And again, it slows down. So we have this perennial issue of speed on inference, which I think NeuralMagic and your team over there is helping to address. So why don't you introduce yourself a little bit and I guess briefly touch on the history of NeuralMagic and how you guys got to where you are today.
Yeah, thanks for the wonderful intro, Glenn. Happy to be here. Yeah, my name is Michael. I've been with NeuralMagic since 2019. Joined here, background in high performance computing, like Glenn said. So worked on making the engine the fastest runtime for CPUs. Really that's what I focus on here at NeuralMagic. And, I think right as you pointed out, Ultralytics has done a great job on being one of those starling libraries that makes it really easy to train models that are accurate. And so people can come up with an abundance of use cases and get started on solving their problems, even with just small Kickstarter data sets. Certainly what we hear from a lot of the people that we engage with in the community and enterprise is they've started to actually get some AI use cases, actually train some real models, not just let's build AI together type engagements. And start to get some ROI, make some money from some of the AI products they have. And now they're worried about the cost, the power, the sort of the complexity of deploying these models, and want to improve on all those things. So I think where NeuralMagic's story really starts is just from the fact of hardware accelerators, GPUs, IPUs, NPUs are really taking like a brute force approach to running these models and dealing with just the raw flops and compute that we need to run the models we have currently. It certainly works from the perspective of training accurate models and just making large convolutions, large matrix multiplications, adding more and more parameters. But we already know from the different model architectures that you make, say within YOLO V5, going from nano to ultra large, there's still useful accuracy at the nano and small level. And these are actually, you could argue, structural sparse ways of modulating these models accuracy in order to trade off those flops for performance, those flops for accuracy. So where neural magic kind of started, it started as, Nir Shavit and Alex Matiev, our co-founders who are professor and postdoc at MIT, are great high-performance computing researchers. They worked on collaborating with some biologists on a connectomics project, sort of mapping the brain out, actually, and found that the brain is, well, really sparse. And so the algorithms they were designing to map out the brain do a lot of sparse computation. So they made up a sparse matrix multiplication algorithm, essentially, and were able to beat out a GPU running a dense matrix multiplication because the brain was so sparse. And it kind of really got them thinking like, oh, well, like we don't just need to throw like raw GPU compute at this. We actually have some like small desktops that could handle this kind of work if we just take into account the fact that the data is sparse. And so it really, neural magic comes from that initial realization that, oh, we can actually do sparse math really quickly. And then the research that's been building over the last couple decades of pruning models and just how sparse can we make models, has been around for decades for just making models smaller on disk. You can store them in compressed formats, or maybe save a little bit of memory, but usually makes no difference for actual performance speed. So kind of the key point is having actual like a sparse matrix multiplication algorithm. And this now plugs in to all the existing sparsity research of pruning models to very high levels while maintaining accuracy, just like quantization is a very popular method for that as well. But we mostly stop at int8 precision at most, because going to say 4-bit or 2-bit, while it can save some space, you're not really getting much faster at that point. So we really work at combining all of these different angles of optimization and compounding them together. So, like the structural sparse methods that the YOLO v5 and YOLO v8 models use at their different scalings, and then quantizing them, and then pruning away 80–90% of the parameters, because while still keeping the structure of the model the same, all the weights aren't necessary to be there.
Yeah. This goes back
so,
to, we've all heard this phrase that we only use 10% of our mind. I think that's been debunked, but you're saying even if we do use 100%, a lot of the neurons simply aren't carrying their weight. They're sort of sending messages which may be redundant, or aren't contributing significantly, and we wouldn't miss them that much.
yeah, exactly. I mean, like, we literally have, ResNet 50 on ImageNet, sort of the gold standard, like the Lin pack of model benchmarks from
Right.
HPC perspective. We pruned that to over 95% sparsity with quantization and still kept less than a 1% relative drop in accuracy from the dense FP32 model. So there's a lot of like,
That's very impressive.
Yeah.
And,
moving it on to efficient nets and YOLOs and BERTs are really promising as well. We're probably not getting to like 95%. Maybe we get to like 85 or 90, but there's a lot of wiggle room, and we're just excited to generalize it even better onto more models.
Okay, that's exciting. And so let me ask some stupid questions really quick. So when I was getting started, a lot of the terminology in AI kind of scared me. So we've got 3 different words here. We've got pruning, we've got quantization, and then we've got sparsification. So could you explain a little bit about each one of those and what they mean and when they might be applied in, say, the training or deployment cycle?
Yeah. Well, first off, I'll make it a little bit easier for you, in that pruning and sparsification
like
are usually kind of together, fusion. Although, like, technically, you could claim quantization is a form of sparsity, because you're changing how you're sampling over like your range and scale of values.
Right, you're reducing the amount of information present in the model, but you're doing it a different way.
Yeah, you're kind of like bucketing things together. Oh, if
exactly
at full precision, you had like all these values from this range, but with quantization, it's now just like one value representing that.
Right. And I've seen that done different ways. Like I played around with a few other toolboxes, and some of them I think they do quantization per layer. So they'll look at the range of the weight values in a layer, and they'll come up with sort of a lookup table, I guess, if you will. And the number of bins in the lookup table is really the bits that you can have. So if you're at 8 bits, then you would have 256 bins in your lookup table, right? And each weight would simply belong into a bin.
Yeah, exactly. There's even things that
Okay.
go per channel, per layer. So you can get
Okay.
more bins of precision there.
Okay.
But yeah, that's definitely where on talking about explaining quantization first, it really is just taking these these floating point values you have, these full 32 bits of information, and trying to crunch these down into, say, 16 bits of information or 8 bits of information or smaller. And usually once you change your range, in terms of now you can only talk about 256 different values versus tens or hundreds or millions of values. You also generate this scale and this shift that tells you sort of where in the range or how wide of a range these values represent. So you still only have 256 unique values, but you can still control, okay, is this covering a really
that's
large,
right. Yeah.
like dynamic range in terms of magnitude of your values?
That's right. With essentially gain and a bias, you apply it to the entire thing.
Exactly. Gain bias. Yeah.
Okay.
Yeah, but
and so I guess this is like easier to get away with during deployment, because during training, we have to compute gradients, which can often be like really small numbers. And so I think we need like a much finer scale there, ideally like a continuous scale. But of course, in compute, there's no continuous scales. But to really get the best derivatives and gradients, I think during backpropagation, that's why I think there's mixed precision, or essentially just FP32 training. So it seems like during training, a higher level of precision is beneficial, but oftentimes you don't need that once you're already done training. You no longer need to calculate gradients and get these like really, really fine values.
Yeah, exactly. And actually, one of the things we focus on for quantization is quantization aware training. So
that's right. It's the QAT acronym. Can you tell us about that a little bit?
Yeah. So for QAT, we're actually generating static quantization. So we're calculating ahead of time during training what those scales and shifts are for that quantized range of values. Versus, and this is opposed to dynamic quantization, which is much more common for post-training quantization or PTQ flows. And post-training is obviously much easier to achieve. You can usually just slap it on your model and just check if the accuracy is affected. But it affects the level of performance you're able to get, because it's dynamic. As your input is coming into each layer, you need to calculate what the scale and shift needs to be based on the actual values that are coming in. And so you waste time just scanning over the data, calculating, like the mean and the square root and all these values, where you can do this ahead of time during training if you just find those right scale and shift values. And the reason you don't do this, you don't really quantize during training, more at the tail end of training, is you still need to find these scale and shift values. And if your weights are shifting, maybe your scales and your gain and your bias shifts. So it kind of just becomes not worth it to constantly be changing all these things that will be locked in once your weights are locked in, which happens at the end of training.
At the end of training, okay. So in QAT, how often are these scales computed? Is it every batch or at the end of every epoch, or how often?
Yeah, it happens at every update of the weights, essentially, so
every update of the weights. Okay, so there's a lot of shifting going on. There's a lot of computing then that's taking place to figure out what the right scale is for every batch.
Yeah, most of it happens up front when you're first. It's pretty dramatic when you turn on the quantization and remove a fourth of the precision, or go down to a fourth of the precision. Then it's those little tweaks that you're talking about, and the scale and the shift are floating point values or in 32 values at the very least themselves. So they have much higher precision in order to translate between these higher intermediate precisions that you need for some operations and the quantized operations that you're trying to reduce the compute on.
Okay.
Yeah.
Okay. It's really interesting.
Yeah. And maybe
So-
I can talk about pruning too.
Actually, yeah. Why don't you? I can talk about pruning for a second.
Sure,
So
yeah.
when I first started YOLO V5, I started writing tutorials, mostly for myself. I had no idea what I was doing, and I thought I should. I was starting to learn things, but I thought I should probably like write some notes, take some personal notes here, in case I need to revisit this in the future. And so I did everything open source. And the funny thing is, it started getting pretty popular, and other people started using it, even as a source of reference, which is kind of ironic because I was trying to basically teach myself at that point. But I did a stab at some pruning and some quantization, and I just used like very basic tools. And so what I did was I went to an initial YOLO model. I think I was probably using YOLO v3 at that point, the PyTorch version that I was starting to build on the Ultralytics / YOLO v3 repo. And I found I binned the values in the weights, and I found the ones that were closest to zero, like maybe like a little on the negative side, a little on the positive side. But I had, I kind of thought about the theory around pruning and quantization. I thought, okay, these are probably not contributing significantly. What happens if I just set them to zero? And so I set them to zero, and I kind of gave myself a sliding scale. Like, let's say I found that the bottom 10% that were closest to zero, and I just turned them to zero. And then I could see that I would lose a little bit of accuracy, but not too much. But the funny thing is, like, the model was no faster, and it's because my matrix was not technically sparse. Like, it was full of zeros, but it wasn't a sparse matrix. It was a dense matrix that I just set some values to zeros. And so my model did not get smaller, it did not get faster, and I lost a little bit of accuracy. And I thought, well, this isn't very fun. This doesn't make much sense. And so I left the tutorial there, and some people have adopted it. But of course, this is not the right way to do it, right? The right way to do it is to optimize the compute, so you're no longer looking at those zeros. And I think this is where the pruning actually comes in, right? You don't just leave the zeros in, but you take them out, perhaps maybe on a channel or a layer basis, so that they're simply not there. So your model is smaller, there's less flops.
Yeah. Yeah. So there's definitely like structural pruning methods like you just laid at the end that most people can benefit from, where you're moving entire channels or changing your like spatial dimensions, or really just removing entire sort of columns or sections, rows, however you want to think about it.
Okay, yeah.
Of the model. But actually you still can get speed up from just having those zeros in the weights.
So turning the matrix into a sparse matrix, but not actually changing the shape of it, will it still give you speed ups? Okay.
Yeah, you just need to change your representation of it.
Right. Okay.
And this is what we focus on,
Okay.
Yeah.
Okay.
And
So
like,
there's structural pruning, and then there's simply, I guess you could say, pruning through sparsification, whereas you turn a dense matrix into a sparse matrix, which is optimized in memory to ignore the zeros. Okay.
Yeah, exactly. And just really like at a certain point, if you think of you're introducing zeros right into your weights, doing some weight sparsity, really anything multiplied by 0 is going to be 0. So you can just skip that computation completely. It's really just about, and people have had sparse matrix multiplication algorithms for a while, but they're more from a research perspective, or they only work when the matrix is 95, 99% sparse. That's when it starts to get a little bit of trade-off. And this,
I remember I've used them, like when I first was in school and I used MATLAB, I started using them, and that was a while ago. So they've been around for a while. I think mostly for linear algebra to speed up matrix multiplications when they were pretty sparse, like you're saying.
Yeah, you get those like diagonal matrices where like
exactly,
values on the diagonal, everything else is zeros. You can
there you go.
One upper half, you can do things there. But it definitely takes a lot of work to make like an industry grade way to run these things in an unstructured way, where it's more you just have random zeros all over the place. But that's kind of the like secret sauce we found, and why we made a whole inference engine around it. And CPUs work really well for this flexibility you need in the algorithm. they don't just have like giant tensor cores that like the latest NVIDIA
Yeah.
GPU have.
I've
So
noticed this trend that CPU performance correlates very highly with the number of flops. So
yeah,
if you take out some operations, you're going to see a speed up on CPU. On accelerators like CUDA devices, that's not generally the case because they're highly optimized for a certain type of operation. And if you do that operation, it'll be very fast. But if you try and apply some optimizations to it, if the operation changes slightly, you're no longer using that highly optimized core, and you don't benefit from those. So in that sense, like CPUs are a bit more rewarding to optimize the model for it, because if you get rid of an operation, you're going to see the effects on the speed.
exactly. And the way we talk about that is that CPUs are almost always compute bound by normal, traditional, dense FP32 models. You can get a little bit less compute by doing quantization or do some structured pruning, but generally, right, if it's just sitting there crunching dense convolutions, they're not really made for this so much.
Exactly.
And so being able to sparsify the model, you get to 50% sparsity, and you're already talking about getting rid of half of the compute. You go to 75% sparsity, that's another half of the compute. You're talking about a fourth now. You go to like 82.5, that's another half. And sort of, especially as you start getting up into the 90s, it quickly keeps having and having, and you get this like multiplicative effect. And you can see some really amazing performance because suddenly the CPU doesn't have to be necessarily compute bound. And this is where you can get pretty far just by making sparse matrix multiplication, but you also begin to kind of be memory bound, which CPUs have their own problems on, simply because the memory, like DDR memory that your laptop or desktop has, is not going to be as fast as like the HBM high bandwidth memory that's going to be on your modern accelerators, because it's like soldered in and like absolutely made to feed these massive compute engines. But CPUs do have a lot of cache, L1, L2, L3, multiple layers of cache, which is basically just super fast memory or SRAM that sits right on those CPU cores, and is orders of magnitude faster than the connected memory. And so what we've done, one of our technologies is called deep tensor columns, is doing layer fusion and taking just sections of the activations and kind of taking that as a column, a subset, and piping that through multiple operations, keeping everything within cache, and then just writing to memory at the start and at the end. And then do this for each one of those columns. And each of these cores gets a lot more effective performance if they're memory bound now.
Okay, so it sounds like you guys have done some serious optimizations specifically for CPUs. And that makes sense, since CPUs are, I think, the most common type of inference backend that we use for models these days. It's not the fastest, but it's definitely the most common out there. And so if you can make some improvements there, then you're having a big impact on the world.
Yeah, we definitely see that, both from just like a ubiquity perspective. It's hardware that's everywhere. Any instance or computer you buy that has a GPU, and it has a CPU also. And you're probably not like utilizing that so much. And so even just looking at like the bill of materials of buying in something or an instance, if you could just use those same CPU cores that are attached to that GPU, it will always be cheaper, if you can get the same level of performance. So that's where we play within, in trying to make that more cost effective, get the performance up to be equivalent, or just even enabling new things where you can't exactly fit a GPU because of cost or performance concerns, because ultimately you still need to power a CPU by the side.
Okay, so
Sure.
let's talk an example of like a real world use case. I like real world stuff. And so let's say I train a YOLO V5 model, maybe like an S model, and I've got all set. I run it. I export it to like Onyx or OpenVINO, and it's got like a bit of speed up on CPU. But I'd like a little more, and I'm paying for like a cloud instance to handle function calls or API requests. So if I can have it run faster, then it's going to save me some money also. what are the steps? How would I use neural magic to take my model and replace it with a pruned, quantized, improved model?
Yeah, that's a great question. Would you mind if I just like showed some of the steps?
Yeah, absolutely. Yeah.
Cool. Yeah, let me just pull up my desktop here.
Okay. And then after that, we'll do a bit of Q&A and answer some of these questions that we've got.
Awesome. Yeah, happy to hear questions. Let me just move this down a little bit. Yeah, so how you would mostly get started is seeing some of our code and our integrations on our GitHub. So on Neural Magic, SparseML is our optimization library for pruning and quantizing and fine-tuning models with all these optimizations and getting them trained in, say, your training framework of choice, either like raw PyTorch or of course YOLOv5. And DeepSparse is our inference engine that actually for deployment we use for running on CPUs and getting that final performance.
Okay, so you export with SparseML and then you run it with DeepSparse.
Right, exactly. Okay. Or if you're training in PyTorch or training in TensorFlow or Keras, you can also export to Onyx, and DeepSparse takes that Onyx format as the open thing. So we're not producing anything that's just specialized for DeepSparse. Your model is still your model. Okay.
So DeepSparse will actually run my Onyx model faster, even if I haven't done anything special to it?
Yeah, exactly, dense models. And I'll show you some of that later on what we're able to do there.
Okay.
So SparseML has a native YOLOv5 integration in terms of bringing pruning, quantization, and sparse transfer learning to YOLOv5. And I actually have a notebook where we've done an example of this. And I've done this all in Colab on a single T4, just on transferring a model onto Cocoa 128 as an example.
Okay.
So first thing you do is you just pip install SparseML with the Torch Vision dependencies, or really just Torch is all you need, and weights and biases. And it'll go ahead and automatically pull all the YOLOv5 dependencies that it needs. So we're also registering our weights and biases little plugin here so we can see our great YOLOv5 results. And then we make simple CLI commands similar to the new Ultralytics repo that's just launched with YOLOv8.
Oh, great.
Congratulations, by the way.
Thanks. It's a work in progress, but it's coming along.
Yeah, it's definitely sick. So, just pointing to the data YAML, the model config, and then pointing to some weights that, if you notice this, this is taking a model that we've already sparsified from our sparse zoo. And that's what this little zoo tag means. So I'll show you real quick.
So you can just point straight to the sparse zoo here. Okay.
Yeah, so this is sparse zoo. And we have a lot of different models across a lot of different domains, computer vision, NLP as well. And we have lots of different bases of models that we've pruned and quantized the various levels. And reporting on all the accuracies and speeds and sizes we're able to produce. So I'll actually take you to where we're looking at detection models. And we have a little, showing all the Ultralytics models we have here. So we have YOLOv5s. We've generated many versions of it at different levels of sparsity. So like the pruned 65% is pruned to 65%, pruned 85 is 85%, and we've quantized it. And the base 9 is simply the dense EPI32 model, the original weights. Maybe that map score will be familiar to you. I know it's an old model. But, and you can also see as we prune and quantize further, we can see that those sizes go down and down. And we also have, YOLOv5L, N, and all these different sizes of models that we've taken the shots at optimizing. And the cool thing
about these guys get a lot smaller when you prune and quantize them.
Yeah, definitely. The quantization kind of cuts it down to usually, a fourth. You're talking about like a 4 times reduction. And then with pruning, sky's the limit. It's really how many zeros you put in there of how much smaller it's going to be. And aside from just having these models here, You know, with the PyTorch weights and the final Onyx that we've been able to create through SparseML. We also have how we actually created the model. And so we have this idea of recipes, which
It's good for
dictate,
reproducibility.
yeah, exactly. So saying that we're going to, prune these weights. So these are like, weights from the state dict and PyTorch. We'll prune these to some level of sparsity. We'll prune these to some level of sparsity. And all this is dictated over, okay, my learning rate's going to change this way. My epoch range is going to be this. And so keeping all this state in a recipe, that's the original recipe. And you can recreate it with, commands that just from after installing SparseML, it'll pull all the dependencies, pull the data sets, and start you down recreating it. And so what I'm going to show you today is focused on transfer learning. So you'll notice the recipe is a lot more simple. Here, we're just taking this pre-optimized model and we put on this constant pruning modifier. So since the model is already sparse, all we're doing is keeping all of the weights that are zeros, 0, and then allowing all the non-zero weights to retrain and fine tune. And throwing out some quantization at the end there.
So this is interesting. So I see this Silu activation. So I've heard feedback that Silu is not the best if you plan to quantize your model. There may be better ways to go, such as ReLU or maybe ReLU6. What do you think of that?
Yeah, definitely. Silu is not a very good activation to quantize. It seems to lose a lot of accuracy if you quantize it. Of course, you can, put in a different activation that's more conducive to quantization, but that also has accuracy trade-offs. Actually, in this case, we're excluding Silu from being a quantized operation. So usually we'll quantize anything we see we can that we think we would see a benefit from. So all the convolutions, most activation functions, and even some element-wise things. But here, because we saw the accuracy goes down beyond an acceptable level, we actually are not touching the Silus at all. And it doesn't give too much of a performance benefit. It's a trade-off. It's something that if you wanted to quantize it and try it, you could just remove these lines and kick off your own training run. But yeah, that's a good eye of, we skipped it here.
That's a good point. Everything is a trade-off in ML. That's what makes it so interesting. It's rare that you find something that is just a win-win situation.
Yeah, definitely.
The question is, what's worth the trade-off? What's the best compromise? So that's a sandbox we try and play in. It's not always clear, but trial and error, a lot of experimentation, I think, is the way to go to gain better insights. You push the bounds in different dimensions, and that gives you a much better understanding.
Yeah, absolutely. And that's where we usually set our cutoff at kind of a 1% relative drop in accuracy from the base model in order to, because otherwise, if you start going past 5%, I've dropped 5% of my accuracy or 10%, you could probably just do like a different type of model at that point. You're talking about a much smaller
Actually,
model.
that's a great question. Sometimes I've wondered if, let's say we start with a large model, you really prune it and it gets to the size of a small model. Is it like, should I just start with a small model in the first place, or is that large model that I pruned down, whittled away, is that going to be better?
Yeah, it's a really good question, and unfortunately, it's always based on the actual numbers you can get.
It's an empirical science. You're right. Just you have to do it and figure out which one's better.
Yeah, we definitely have some things that prove that. You can get past the original dense model's performance if you take a large model and pruning quantizing it really far, and you can still even get more accuracy and more performance than the smaller model. But then also you could prune and quantize that smaller model and give it even more accuracy or even more performance out there. It's really about what do you look at? Do you have some minimum accuracy that you're trying to hit, and maybe going from above and optimizing, sparsifying down would be better. yeah, it is kind of specific and nuanced, but it's certainly we're building the tools for it. We're selling the pitchforks, I guess, for
Yeah,
optimizing
yeah,
your model.
yeah. Same here.
Yeah, so I guess just like taking this example, I think just going through the, just kicking off, plugging this really in here into this collab. I won't bore you with the actual training since, it's a lot of stuff and it's the usual stuff you would expect from your friendly YOLO v5 repo. So all of your weights and biases stuff, and your model layer printouts. And you can actually see that we're able to log this training run in weights and biases, like you would normally do with YOLO v5, just through that little weights and biases login from before. And you can see, we're from that we showed you in the recipe, we're modulating the learning rate to make sure the fine tuning goes smoothly. We can look at the original labels of the match and look at what was predicted. And you can see your usual F1 precision recall curves. And you can see and make sure that the model, as it's fine tuning, is getting to a decent accuracy and is leveling out. So you can keep up with the state of your ML experiment, even when you are sparsifying and optimizing it. And just as a check, we can also see the different sparsities of the weights. And so here we're actually pruning different layers to different levels, because some layers are more sensitive in terms of what their allowed sparsity is, or rather, if I sparsify one layer, it's not going to affect the accuracy so much, but maybe I should also sparsify it because it actually has a greater impact in terms of flops or performance. And so these are a lot of the algorithms that we publish. Actually, one of the things you mentioned in your sparsity research, your pruning research, is really similar to a method we call magnitude pruning in the literature. And it's really about, pruning all those weights that are really close to zero and slowly increasing that threshold or that magnitude over time. But basically just, if it's close enough to zero, we just set it to zero and then let the model retrain. There's other methods that we call first order or second order methods that basically take approximations to figure out, okay, I look at this parameter, actually, how much of an impact does this have on the final loss of the model if I take it away, if I remove it? And these things allow you to much more fine-grained and intentionally remove parameters while knowing what their impact on the accuracy and the final loss and accuracy are going to be. So this allows, there's some of the things that allow us to make these models so much more sparse over time.
Let me ask another stupid question. When you take out values by setting them to zero, do you ever compensate that by adjusting nearby values to bring that back up to what the lots used to be? Is that a valid strategy, or is that too much work?
No, yeah, it's part of the it's really how much computation do you want to spend for each parameter. So you could absolutely do a full multiple backward passes in order to figure out, okay, if I took this parameter away, what would this be like? If I took this one away, what would it be like? Of course, this is going to be too slow, and it's going to extend your training out massively if suddenly you're running 100 backward passes where you're just running one. So really a lot of the complexity, aside from the research and we can make better algorithms, it's the most accurate thing ever. What's actually realistic and not going to be a nuisance every time you want to do it to your model. So that's
this is where we get back to the recurring theme, where you need a compromise between your competing interests. One of them's training time. So you could have the very best model in the world, but it would be so impractical to train and use that it's just not very worthwhile. So, makes sense.
Exactly. Yeah. And so just showing that, we've trained the model. We also have scripts to export it to Onyx. So just pointing to the final PyTorch weights and exporting it with dynamic size here. So same YOLO v5 flow using that export.py. And showing you, the difference in compression. Here we have the original dense PyTorch weights dense and unquantized, showing over 29 megabytes on disk, and then exporting the model to Onyx, which has the whole folded quantization, everything in there. And then showing what that Onyx compressed is, getting it down to 2.9 megabytes, which is exactly 10 times less than the
That's a lot
original
smaller. Yeah,
and small.
that's impressive.
So it definitely makes a difference. And then showing how you would deploy this model, pip install DeepSparse with, the extra YOLO bits we throw in there.
Okay.
And we'll pull an example image from GitHub. And then we have a nice CLI for annotating with object detection, where you feed it the Onyx model we just produced in that image. And you can see, it can throw some boxes on there and do some decent performance.
Okay, so we've cut out 90% of the model, and it looks like it's still doing a great job at detection.
Yeah.
And it's a lot faster too. So that's impressive.
Yeah, definitely.
What about the actual pruning quantization time? Let's say I take a day to train my 5S model. What's it going to take to prune and quantize it to this level to make it 90% smaller?
Yeah, so that's actually kind of the magic of sparse transfer, is that we've done the cost of pruning the original base model trained on Cocoa. So from that case, you're actually taking that model and fine tuning it in the same amount of time you would fine tune from a dense model from YOLO v5. So if there's already an architecture that's been sparsified, you can just take that and fine tune it in the same time you would fine tune from a dense model, which is really cool. And we have some really cool papers that show that this works pretty well. And actually the sparsity, definitely at the medium levels of sparsity, can actually help the generalizability of these models for fine tuning. And
that's interesting. Okay.
Once you go to the really sparse levels, then it's okay, how much accuracy are we willing to trade off on the fine tuning task? But yeah, at those kind of like 70, 80% levels, yeah, we have this really cool paper called How Well Do Sparse ImageNet Models Transfer, focusing more on ImageNet and image classification. But it can actually help with the generalizability, because each of the remaining weights are having to work a little bit harder, generalize a bit more. Yeah.
So, okay, so you're saying I can show up with a pre-trained model that I've done myself, but if I started training from one of the Model Zoo models, it's already sparsified, and then I can benefit from that directly. So there's this whole other field of pre-training from a sparsified model that I can download from the zoo.
Yeah, but also if you want to sparsify models from scratch, we're experts at this, but also it's all open source. Like we have guides and documentation on how we've done it ourselves. And you can take a lot of the recipes that we've created on the Sparse Zoo and take your own notes from them and begin to apply them to your different models. Looking at these pruning modifiers, we have some specific weight names that we've obviously gotten from the model we're talking about, but starting to substitute them out for your weight names and maybe mess with the final sparsity values or the epochs that you're training over or the learning rate. It's pretty flexible, and that's why these recipes that are here for every single one of these models make a pretty good learning base, or like a library of optimization, so you can do these experiments yourselves.
And do the recipes generalize across dataset domains relatively well? Like if the recipes are built off of Cocoa and I have, say, a medical data set, would I still be safe to kind of start from that, use it as a starting point?
Yeah, they're basically the same. You're probably going to want to change the learning rate and the hyperparameters like the same way that you would.
But you would anyways, depending on the size of your data set and so on. Yeah. Okay. Interesting. This is really informative. Actually, I've learned a lot here. So
yeah, and just one more thing I wanted to show is we work with YOLO v8, and you talked before about what kind of the engine could do in terms of just being better dense performance before we've gone and optimized the model. So here we actually ran some numbers on YOLO v8 Nano, seeing really how many frames per second we could crank out. And this is even batch size 1. We can crank a little more with batch size 32. But sort of the second to highest bar, DeepSparse, is running the exact same model as Onyx runtime and PyTorch, of course, exported to Onyx. So it's the same exact map, and we're able to be, that much faster. And
without any changes to the model, just using a different runtime.
Right, exactly.
Okay, that's very impressive.
Quantization, able to push that even harder to get that, basically 10x speed up. And here
so you mentioned,
yeah.
You mentioned batch sizes, and I saw a user had asked a question, or one of the viewers, about whether CPU inference is exploiting parallel cores. So if let's say I have like an 8-core laptop, and I run a batch size 8, is that, or a batch size 1? Like, what happens there on the back end?
Yeah, definitely more batches allows for more parallelism, but I wouldn't think about it so directly like that. It's more about at batch size 1, can we generate enough work? Is there enough work to do to use all of the cores available? So for instance, running batch size 1 on YOLO v5n, maybe you don't have enough. You maybe have enough to saturate like 4 cores, but 8 cores maybe a little less.
Okay.
But then if we go to the large model version or extra large, at batch size 1, we're going to have plenty of work to saturate all those cores, and it won't matter too much whether it's batch
at
size
that point,
size 8.
Okay, yeah, I see what you're saying. At that point, it's not going to matter if you increase your batch size.
Yeah, there are different approaches you can take if you have a large enough batch size in terms of exploiting parallelism. Like you can very directly, like I'm sure this user is, the commenter is thinking about, you can just put different batches on different cores. But
yeah, I think that's what we're all thinking. Yeah. But it sounds like it's already being optimized. Like we don't need to take any additional steps, and the inference is parallelized, not so much in a per image basis, but maybe per channel throughout the model.
Yeah, exactly.
Okay.
Yeah, you got it.
Okay. All right, that makes sense. So let me take a look at some of the questions here. And okay, let's see here. So I saw, okay, Fabio is asking about clip models. Let's see, do you guys have clip inside the model zoo? Or if not, I guess what would it take to get there? So clip is transformer based. And I guess the other inherent question here is whether transformer models enjoy similar speed ups and similar reductions in size as convolution based networks.
Yeah, definitely. We've actually seen some of our best raw speed ups from transformer models. You can check out some of our blogs here. I won't do you the disservice of talking about NLP too much on this. But we've done a lot of work on especially like BERT models and T5 encoder decoders, and we have some research. We have a paper called, if you're familiar with CLIP, you're probably familiar that it's a vision transformer, or VIT. We have a paper called OVIT, which stands for optimal vision transformer, and that's just applying some of our pruning methods of how we've been able to prune some of those models. We focused more on the ones that are more focused for edge inference, like DEIT or efficient former. But there's really no reason not to put it onto clip. It's just a matter of priority and what we have people asking us for the most.
Okay.
Yeah.
Okay. And let's see, we've got another interesting question. We've got Joshua here asking, how does the platform compare with NVIDIA DeepStream? Does SparseML use Python at runtime or C++?
Yeah, so SparseML is the training optimization framework. So it's pretty much all in Python in order to play nice with PyTorch and your original training framework. DeepSparse, the inference engine, has Python bindings. Obviously, you can pip install it. It does also have C++ bindings. And the core engine is written in C++ and assembly. Because
assembly.
once you actually get to these edge deployments and embedded devices, you don't really want to mess around with Python interpreters and garbage collection and things like that. So yeah, definitely parity there. Yeah, on the assembly part, the engine actually is basically a model compiler, in terms that it takes these Onyx models, these Onyx graphs, and compiles them down straight into binary code in terms of and plans out how we're going to execute it. That's part of the reason why it's able to have such control over, oh, do I use like this core's cache to do this thing and fuse this thing this way? It really boils the model down onto the hardware, onto the hardware that it sees that it has available. So
Okay.
it's cool. Love to talk more about it.
Okay. And then I see a question that I can answer. There's one by SY. He says, will this be recorded and shared? And yes, this is going to be available right after we're done here. So the live stream ends, but then it just becomes a normal YouTube video. And then you can just watch it whenever you want. The comments, unfortunately, seem to disappear. We can't figure out how to keep them. So all these fun questions are going to go, but we'll still have the video. And let's see, somebody, okay, finally, we have a request for YOLO V8 to make an appearance in the zoo. Is there a time frame for that or roadmap that you can share with us, Michael?
Oh yeah, yeah, it's a high priority for us. I think if you actually look on DeepSparse, we already have some pull requests that one of our ML engineers is already working on an official pipeline integration, which is really cool. Better than the example folder I made for the blog. That's really kind of just me hacking things together with your new NMS and Ultralytics. But yeah, basically like a month or so, we expect to have a whole range of the YOLO V8 models, from nano to extra large. So yeah, expect that in the next month or so, to be on there, kind of coinciding with our 1.5 release.
Okay.
Yeah.
All right, interesting. Let's see, we've got another couple of questions here. So there's an edge computing question by Joshua Holtz again. He's asking about the relative speedups on ARM. So for example, I myself do most of my work on a M2 MacBook Air. And Michael, you mentioned before, you're also on a MacBook. So do sparse models and Onyx models enjoy similar speedups as they do on Intel hardware?
Yeah, so DeepSparse currently runs on x86, so Intel and AMD. And we're about to open up ARM support for it. And we're actually starting with more server class stuff so that you can easily get in the cloud. So AWS Graviton and say Ampere also makes server class ARM chips. But spoiler alert, it also runs on M1 and M2 MacBooks. So I've actually run a few demos. I was at NeurIPS at the end of last year. And we had sort of an early preview build running on my M1 MacBook, actually getting some pretty good performance. We're still not super locked in on like where the absolute performance is going to be for, in terms of like what the actual frames per second will be on ARM. Also, there's a lot more ARM chips and platforms to consider. But the relative performance is there. I'll say that, and we're really excited that hopefully we'll have some good YOLO numbers on a Raspberry Pi in the near future is my hope.
Oh, great.
Yeah,
I'm a big fan myself of ARM hardware. I think they've done a great job of minimizing energy consumption, and the companies that work on top of the architecture, like Apple, have done a great job of using it to create very performant chips, not just that are fast, but that don't use up all your battery. So.
Yeah. Y'all's mobile app for running these models works really well.
Yeah, well, it's so the very first mobile app that we had, I wrote myself, and I'm not quite sure how I did that because I'm not a mobile developer. It was a painful process, but after all that work, the YOLO models that I had at the time, and this is about 4 years ago, could barely run on the iPhones of the day. We were getting something like 1 or 2 or 3 frames per second, and it was just not something anybody would download from the store and really enjoy using. And it's changed so much just in the last few years. The TOPS and the ANEs that Apple has in there that they've sunk effort into and dedicated space on the ASIC for are very impressive now. So things are changing really fast around here. It's one of the reasons I like the field so much.
Yeah, it's definitely like
Okay,
orders of magnitude every
yeah,
couple.
literally orders of magnitude. Yeah, I think like the very first ANEs that Apple had, I think 5 years ago were less than one top, and now I think they're over 15. So yeah.
Yeah.
Okay, so let's see. We've got a security question from Akash. He says, while running application using YOLO v5 during SAST checkmark scan, it gives high severity warning. So I'm not, this is probably directed at myself. I'm not a security expert, and I'm not really familiar with what SAST checkmarks is. But if you have like a technical concern, I would direct you to raise a bug report or simply ask a question on the repo. Or actually, I think GitHub has a special channel for security concerns. I think
Yeah,
there's a way to raise those.
yeah. I'll have to check it out myself. I mean, I know SAST stands for Static Application Security Testing.
Okay.
Yeah, testing. So yeah, I'd really have to know what you're looking for there in your test, but you know, it could be simple things like just, oh, you know, API calls it's making to check in with weights and biases or check in for version checks. But you know,
Could be. We've got we have like all the default GitHub code scanning tools in YOLO v5. So these are run monthly, and right now nothing is showing up here. I think it's called code QL. So
yeah.
But again, definitely raise an issue. Give us like a reproducible way to see what you're seeing, and we'll take a look at it. Okay. I think that's it. Let me look at these questions again. Okay. Yeah, I think we're all covered here. So we're rounding out the hour. It's been a little interesting. I've learned a lot today. I hope everyone else has also. And I'm looking forward to experiment with some of these sparsification quantization tools. So thanks a lot, Michael. And if you guys have any other questions, of course, feel free to leave them on GitHub for myself or Michael. Raise an issue, ask a question, and get in touch. So thanks a lot.
Yeah, thanks so much. Take care.
Okay, thank you. Bye, everybody.